Hey everybody, it's Richard here. I'm going to talk in this lecture about individual participant data meta-analysis projects and how we do this statistical analysis. Two-stage or not two-stage. Thanks for various collaborators that have worked with me on this methodology issue over the years. Let's get on with it. Okay, so what is a two-stage approach? Well, two-stage approach takes the individual participant data that we've got from each of multiple studies, and in the first stage, it will use the IPD from each study separately to derive aggregate data. So, for example, we would fit a linear regression for continuous outcomes, logistic regression for binary outcomes, Cox regression for survival outcomes, and we'd obtain, let's say, if we're looking at trials, a effect estimate, like a treatment effect estimate, and its confidence interval or variance. And so that's our aggregate data in the first stage that we've derived from the IPD ourselves. And in the second stage, we are going to pull that aggregate data using, well, traditional standard meta-analysis techniques, such as an inverse variance, weighted, common effects, or random effects model. The Stata module IPD meta does both of these stages for you very, very quickly. And the second stage uses, like I said, familiar meta-analysis methods, but they typically assume that effect estimates are normally distributed and that variances are known. So there's a little bit of a concern there. In a one-stage approach, we actually now analyse the individual participant data from all the studies simultaneously. And we do this in a hierarchical multi-level regression model, also known as a mixed effects model. What this means is that we're accounting for clustering of participants within studies, or we should be accounting for clustering if we're doing it properly. So, for example, we might have a separate intercept for each study. And then we've got flexible options like, how we stratify nuisance parameters, such as adjustment for prognostic factors. Do we adjust them by study? Maybe we put random effects on those. Equally, we could put a random effect on the intercept. But the key parameter of interest, so it could be the treatment effect again, like I mentioned before. Again, we would assume either a common effect or a random effect on that key parameter. So we're analysing all the data in one go and accounting for clustering and potentially accounting for nuisance parameters by also stratifying those by study. But the main parameter of interest is either a common effect or a random effect, like we would do in a standard meta-analysis. So either approach is going to lead to a summary effect of interest. So the question is, which is the right thing that we should be doing? So many theoretical and empirical papers actually say that the results from one-stage and two-stage methods are usually similar. So, for example, Stewart et al. One-stage statistical analyses may not add much value to simpler two-stage analyses. Bowden, for survival outcomes, there appears to be only a very small gain in fitting more complex models that are one stage. And Morris et al. For continuous outcomes, the number of stages used to fit this model is irrelevant, provided the same underlying model is used. Inference from one-stage and two-stage procedures practically equivalent. So very strong statements about them being similar. But actually, is this always true? We'll come back onto that, but let's have a look at an example. So let's have a look at an example. Individual participant data meta-analysis of hypertensive drugs. And so we're looking to see whether these drugs lower blood pressure. And we have, therefore, a continuous outcome of blood pressure. And in this example, we have 10 trials. And therefore, the two-stage approach is going to fit in the first stage a linear regression in each trial to obtain the treatment effect, which here is a mean difference in blood pressure comparing treatment versus control at follow-up after adjusting for baseline. And in the second stage, we're going to pool the study-specific estimates of the treatment effect, i.e. the mean difference in blood pressure, and we're going to account for the variance of those estimates as well using a random effects meta-analysis, a traditional random effects meta-analysis using restricted maximum likelihood estimation. The one-stage approach is going to use, again, a linear regression, but it's going to be a mixed effects linear regression. It's going to analyse all the IPD from all those 10 trials all together. We're going to stratify by study the intercepts, the baseline adjustments, the residual variances. These are all nuisance parameters. We're not going to make any assumptions about the relationships across studies because we're going to have separate terms for each of those in our model, but we're going to pool the treatment effect using a random effects model. So we're going to get the average treatment effect that we're assuming has heterogeneity across studies, and so we're looking to work out the average of those treatment effects. And again, we're going to use REML estimation, so consistent REML estimation used in both approaches. Okay, so what do the results look like? So here's a forest plot, and on this forest plot I've got the 10 studies, and I've got the results of each of these 10 studies denoted here by point estimates and confidence intervals. Then at the bottom we have our summary pooled meta-analysis results from the two-stage approach and from the one-stage approach. What do we see? Well, they're basically identical. Very similar pooled estimates and confidence intervals. So this comes back to that previous slide where people have shown that these approaches are very, very similar in most settings. And the weights of each studies are similar, and therefore we are confident that we could, in this situation, choose either of these two approaches to use to present our results. So why are they similar? Well, actually here, what's happening is that each trial is quite big, about 200 people at least in each trial. So remember what I said about the second stage assumptions, that we have estimates that are approximately normally distributed with known variances. Well, when the trials are reasonably big, that's going to be a good assumption to make. Both approaches, whether you do one stage or two stage, are going to stratify nuisance terms by study. So we're making consistent assumptions. We're also making a consistent assumption about a random treatment effect. Like I said, all methods use REML estimation, and I've used wall-based confidence intervals, so plus or minus 1.96 to derive them. So same assumptions. The assumptions for the two-stage approach are valid. Same estimation methods, same methods to derive confidence intervals. So given all that, it shouldn't really be surprising that we're getting similar results. So the key message, therefore, is that if the data are not sparse and you get non-negligible differences between one stage and two stage, then actually what I would say is it's you that's doing something wrong. It's not that there's a problem with a one stage approach or a problem with a two stage approach. It's probably the problem with what you're doing. That is that you're making different assumptions. So you may be saying that one stage models are not accounting for clustering, or some terms in there that you're not stratifying by study, but in the two stage you do. So the compatibility of those two approaches is not the same because you're not forcing them to have the same assumptions. Maybe you're using different estimation methods. So you may use REML for one method and maximum likelihood for another. Or maybe disseminating and lead, the default approach to most meta-analyses in Cochrane, for example. You may use a different method for calculating confidence intervals. So usually the cause is you and not one stage or two stage per se. It's because you're doing something to make them different. Alright, so I could end the video here, could I? Well, actually no, because there's also a counter argument. And this is shown by some strong advocates of the one stage approach. Right, so Matthew and Nordstrom, for example, they say there's significant loss of precision from using a two-stage approach. Contepantelis, a fully specified one-stage model should be preferred. Steinen, we would prefer the one-stage approach wherever it's feasible, especially advantageous if the events are relatively sparse. Right, first thing to say is that those two first references are not recommended. Those conclusions do not have any weight. In the first situation, it's a very simplistic situation, which wouldn't actually occur in reality. So have a look at that paper and my references at the end if you want to look at that more. In the Contepantelis paper, again, the assumptions of the model are not right. They are making assumptions that lead to the one-stage model having lower standard errors when that is not justified in reality. So I want us to focus on the Steinen paper because I really like this paper. Especially advantageous if the events are relatively sparse. So let's just look at this in a bit more detail. So let's have a look at an IPD meta-analysis of trials of hormone replacement therapy. And specifically, I'm going to use maximum likelihood estimation. I'm going to stratify intercepts by study, and I'm going to use wall-based confidence intervals. So my estimation method, my nuisance parameters, and my confidence intervals are all consistent between the two approaches. I've got 7 studies. This is a binary outcome now, number of cardiovascular disease events, and the trials you see are quite small. Apart from this number 1, most of the trials are reasonably small in terms of numbers of participants, but crucially, all trials have sparse numbers of events. So most trials have 0 in the control group, or 1 or just a few even in the treatment group. So what that means is that, remember we talked about the fact that in the first stage of the 2-stage approach, the assumptions of normality of my effect estimates and known variances, well, because of the sparse data, those assumptions are going to be very, very poor. So we might expect here to have differences between 1-stage and 2-stage, and indeed that's what we see. The 1-stage approach gives an odds ratio of 1.74, 2-stage 1.31, so big difference in the summary estimate. So what's happening here? Like I said, it's about sparse data, the 0 events, and the 2nd-stage assumptions being invalid. To use the 2-stage method here, I've had to use a continuity correction. So in brief, adding like 0.5 to every cell of that 2x2 table defined by number of people in each group and the number of events. The 1-stage approach doesn't need to do any of these things. It can handle 0 events in one of the arms. So it can handle the sparsity of the data, doesn't need to make any assumptions about within study normality and known variances, and so is more exact. And that's why the Steinem paper is great, because it really emphasizes that with sparse data, the 1-stage method is preferred. Okay, so you could then say to me, well, let's just use a 1-stage approach all the time. Well, again, I don't advocate that either. If you do that, and you tell people to always use a 1-stage approach, I think you're going to be throwing yourself and maybe those other people into the fire, because the 1-stage approach is itself not a panacea and mistakes await. So let's just have a look at some of these things to finish. First of all, what tends to happen is that people forget about the nuisance parameters. Remember I said to you at the start, it's because in situations with big data, you should be expecting 1-stage and 2-stage to be similar, and often you don't see that. It's because somebody's doing something wrong. And what tends to happen is that the 1-stage models are being fit wrongly. So, for example, if you were to use a 1-stage model, then the software will not automatically stratify nuisance parameters by study. So, for example, they would assume a common residual variance. So each study has the same residual variance. Or they wouldn't even account for clustering properly. Let's have a look at this just in terms of the residual variances. For a 2-stage approach which automatically assumes a different residual variance, we get a summary result of minus 10.17. For the hypertension trials, the 1-stage method, if we make the same assumption, we get basically the same result. We've already seen that in the forest plot earlier on. But if the 1-stage model assumed a common residual variance, we now start to see a difference again. We have a larger treatment effect and a larger estimate of between study heterogeneity. So the change in the assumption of the residual variance is having an impact. Same issue will apply if you make different assumptions about the intercepts, about prognostic effects. Not stratifying or conditioning by trial will lead to different results, and it could be big in some situations. The trouble is that when people fit these models, they don't really understand a lot of the time what assumptions they're making. So be proactive in your research to know what assumptions you're making. Okay, so another area that I've mentioned is the choice of estimation method. Remember earlier on we talked about the hypertension example and using REML estimation. Well, if we use REML for both 1-stage and 2-stage, we get basically the same results. But if we'd used maximum likelihood estimation with the 2-stage and REML with the 1-stage, we start to see a difference in the pooled estimates. Not much, but certainly a bigger difference in tau squared. Similarly, we may have used a 1-stage with a REML and a 2-stage with a traditional disseminant layered estimate, and now we would see a lower summary estimate and a much lower squared estimate. So the estimation method has a big difference. And again, by default, different packages use different things. So if the estimation method changes, it can have a big impact. Notice here that I've also got the maximum likelihood with centering. That's a nuance that's worth mentioning here, that centering is important to reduce downward bias and maximum likelihood estimation. If you didn't center, then this is what you would get. Again, you would have a lower treatment effect estimate, not by much, but again, a much lower squared estimate. So whether you center covariates by their mean does have an impact on the estimate of squared. So covariate centering, let's go back to the hormone replacement therapy IPD meta-analysis with the 7 trials. Before I didn't mention about centering, but if we were to use a one stage with centering, we get 1.91, but a one stage without centering gets 1.74. Crucially, with the 1.91, we also get an estimate of squared that's 0.57, where it's estimated at 0 without centering. So that again is due to this downward bias if you don't center. We talked about the issue with the 2-stage before. So centering in a one-stage analysis with maximum likelihood estimation has a big impact. And again, this leads to problems if you don't deal with it properly. Another nuance related to this is the fact that most software for binary outcomes would use maximum likelihood estimation. But actually, we can use REML estimation if we're willing to assume a pseudo likelihood. So most packages don't have this, but you could use ML-Win, for example, or you could use a Bayesian approach, which would circumvent this issue entirely. But by using REML, that's deliberately to overcome this downward bias in the maximum likelihood estimation. So if we use REML, whether we use stratify the intercept or a random intercept, we can see that the downward bias here is lower. It's not 0, but it's much lower than using maximum likelihood estimation. And this is from results of a simulation study through our work. So again, some subtleties here that if you use maximum likelihood estimation, then you should center to improve results. So reduce the downward bias. You see it's reduced there down to about 50% compared to nearly 100% if you don't center. But you can do even better, at least with large data sets, when you use REML, because the downward bias is reduced even more. So, okay, big decisions with one-stage models, and whether you center, use maximum likelihood estimation or REML estimation, which most people don't know about. Lastly, the example of ecological bias or aggregation bias. Here we're looking at the hypertension trials again, and we're saying, is there a difference in the treatment effect between males and females? I'm looking at the overall treatment effect in a trial against the proportion male in the trial. And the solid line is the meta-regression, which shows you that there's a very strong association between the proportion male in the trial and the overall treatment effect. In fact, the overall treatment effect is reduced as the proportion male increases. But that's the across-study association. The within-study association, which is the individual level, we're looking at the difference between males and females. That's depicted by the gradient of the dashed lines. And we see that nearly all the trials, particularly the bigger ones, the gradient is pretty flat, which means that there's no difference between males and females in the treatment effect, contradicting the across-study association between the average treatment effect and the average proportion of male in the trial. What does this mean? Well, this means that actually in a one-stage model, if you just fit an interaction term between treatment effect and sex, then you will amalgamate the across-study relationship with the within-study relationships, and therefore it would distort the within-study relationships. But in a two-stage approach, you don't have that issue because you're just estimating the within-study relationships and pooling those. So this is aggregation bias in a real example, and one-stage models would have to forcefully separate out the individual and across-study level effects, and most people sadly don't do that and therefore introduce errors. So what does this mean? This means that one stage flexibility is actually deceptibility. Flexibility to me means that many people start making modelling mistakes and making strong and wrong assumptions. It's deceptive because actually the two-stage approach can be more flexible. It's quite easy to handle cluster trials, crossover trials, and parallel group trials in the same analysis. Whereas in a one-stage model, trying to handle all those together would be quite challenging. It can also handle studies where IPD is only available remotely, so you can't actually have it all in-house, but you can analyse it remotely or extract summary estimates remotely for those studies and then pull them in the second stage with the other studies that you do have IPD for. And even bespoke one-stage models that people sell as being a panacea can often be replicated in a two-stage model. So, for example, you could have a multivariate framework in the second stage, which accounted for all parameter correlation from the first stage. And we can place distributional assumptions on nuisance parameters, for example, intercepts, residual variances, even in the two-stage approach through that multivariate framework. So one-stage models, people tell you that they're more flexible, that they're panacea. They're not. Yes, they're relevant for sparse data and important for sparse data, but we need great care when fitting them. So that's the message. In summary, two-stage or not two-stage. If most studies are small, so you've got few participants or few events, definitely use a one-stage approach. Else, I think you can choose whichever approach you want, but neither is a panacea, and carefully follow best practice. One-stage models need much care, and really you need to have professional statisticians working on that modelling to make sure it's done correctly, and certainly people with experience in IPD meta-analysis modelling. I've given some available code at ipdma.co.uk to give you a sort of a starting point. One-stage models and the complexities are not well recognised. Like I said, centering covariates, separating out within and across study information, REML or pseudo-likelihood approach rather than ML approach. All these things need thinking about. If data are not sparse, then usually I would say just use the two-stage approach. For example, using IPD meta-analysis data, it's going to give you nice summaries using methods that are well known that you're probably used to using in the second stage, and nice graphical displays like forest plots and funnel plots and things like that. So that would be my recommendation. Okay, thanks for listening. If you want more details, go to our main paper that was published in Research Synth Methods. Two-stage or not two-stage, that is the question. Have a look at our textbook, which has got the full technical details of all these issues that I've talked about. And also maybe check out our website, ipdma.co.uk, and our online courses, which run each year from the University of Birmingham. Thanks very much.